Next example is prove that if sequence mod Sn, if sequence mod Sn where n runs from 1 to infinity converges to 0, then sequence Sn where n runs from 1 to infinity converges to 0. Okay, so example says that if mod of Sn, sequence mod Sn is converges to 0, then their sequence Sn is also converges to 0. Okay, solution of this, how to prove this, how to proving that this example here given that firstly given that sequence mod Sn where n runs from 1 to infinity, okay, is converges to, this is short form of converges to 0. Okay, that is this sequence has limit is 0, which implies that limit n tends to infinity mod of Sn. Okay, this sequence mod of Sn, their limit is 0. Okay, so their limit is 0, which implies that by epsilon n definition for all epsilon greater than 0 there exists integer belongs to I, there exists positive integer I such that mod Sn minus L, mod Sn minus L is less than epsilon. Okay, which is less than epsilon. L is here 0, limit is here 0. Okay, limit is 0, less than epsilon whenever n is greater or equal positive integer n. Okay, so this mod is simplifying, then mod Sn, okay, is less than epsilon or all n is greater or equal n, which implies that their value is mod Sn means mod Sn is less than epsilon whenever n is greater or equal n, and this Sn is can be written in the form of Sn minus 0 is less than epsilon for all n greater or equal n, and by definition of epsilon n definition, Sn mod Sn is less than epsilon whenever n is greater or equal n, means at least here one positive integer exists such that mod Sn minus 0 for all epsilon greater than 0. Okay, therefore by definition of epsilon n definition, by epsilon n definition, Sn has a limit is 0. Okay, by epsilon n definition, limit n tends to infinity, Sn is equal to 0. Okay, this is the proof of our example. Okay, so how to proving this? Only to consider epsilon n definition, only to using epsilon n definition consider mod Sn minus 0 is less than epsilon. Okay, and lastly to we get only rearrange this and mod Sn minus 0 written in the form of their mod Sn minus 0 written, their 0 this term and this term are same. Okay, so only to write Sn minus 0 is less than epsilon whenever n is greater or equal n. Okay, this is our proof of our example. Then next example is for any AB belongs to R, show that R means set of real number, show that mod A minus mod B mod complete is less equal mod A minus B. Okay, and using this, then prove that sequence mod Sn, where n runs from 1 to infinity, sequence mod Sn converges to mod L, converges to mod L if sequence Sn, n runs from 1 to infinity, converges to L. Okay, here in this example, firstly to prove that mod of mod A minus mod B mod complete is less equal mod A minus B, and then using this result to show that mod of Sn is converges to mod L if Sn is sequence converges to L, means this sequence is converged to L, then prove that mod of Sn is also converged to mod L. Okay, so limit is given that L in this sequence. So firstly to prove that mod of mod A minus mod B is less equal mod A minus B. Okay, let firstly consider that mod A can be written in the form of mod A minus B, plus B, add and subtract only B. Okay, so add and subtracting only B, then by using triangle inequality, triangle inequality means A plus B is less equal mod A plus mod B. This is triangle inequality. Using this triangle inequality, this is suppose that A and this is B, then by using triangle inequality, this is less equal for mod A minus B plus mod B. Okay, using this triangle inequality or using this result. Okay, and therefore this mod B or subtract mod B from both sides, we get mod A minus mod B is less equal mod A minus B. Okay, so this is one, this is suppose that equation number 1. Okay, then this means that here firstly this term how to show mod of mod A minus mod B mod complete is less equal mod A minus B, how to show, if using this result mod of x is less than 1 whenever minus 1 value of x is lies in between minus 1 and 1. In this here mod of mod A minus B, how to show mod of A minus B is less equal mod A minus mod B. Okay, and this is less equal plus mod A minus B. Okay, so when you show this equality, then we say that this mod of mod A minus B is less equal mod A minus B using this result. Okay, so one part is completed, mod A minus mod B, mod A minus mod B is mod A minus mod B is less than mod A minus B. One part is completed. Second part is to show that minus of mod A minus B is less than mod A minus mod B. Okay, so for second part, similarly define mod B. Similarly define mod B is equal to, put add and subtract A. Okay, B minus A plus A we get, then by using triangle inequality again by using triangle inequality, their value is B minus A plus mod A mod B minus A by triangle inequality. Triangle inequality is, this is triangle inequality, mod of A plus B is less equal mod A plus mod B. Okay, so then here mod separating this term. Okay, so or subtract this term in this term. Okay, then mod B minus mod A is less equal mod B minus A. Okay, then here minus sign is common, remove minus sign is common, then minus of mod A minus mod B Okay, this is here also common minus sign, we get mod of minus minus of a minus b. Okay, then we can return in the form using this result mod ab is equal to mod a into mod b. This result using here minus 1 into a minus b, so mod of minus 1 into mod of a minus b, this is less equal mod a minus b, because mod of minus 1 is 1. Okay, and here minus of mod a minus mod b, minus of mod a minus b is less equal a minus b. Okay, minus mod of minus mod a minus mod b is less equal mod a minus b, and therefore multiply by minus sign, we get sign is changing. Here we get multiplying by minus 1 in both sides, we get minus minus plus, we get mod a minus mod b, which is greater equal minus of a minus b. Okay, and this is equation number 2, and therefore from 1 and 2, therefore from 1 and 2, here from 1 and 2, one is mod a minus b, mod a minus b is less equal mod a minus mod b, and second is minus of mod a minus b is less equal mod a minus mod b. Using these both we say that, which imply that minus of mod a minus b is less equal mod a minus mod b, mod a minus mod b, sorry, here greater equal. Okay, mod a minus b is greater equal mod a minus mod b, and then this term is less equal mod a minus b, and therefore using this result minus 1 is less than x less than 1, which implies that mod x is less than 1, less equal, okay, less equal 1. Using this result here mod minus a minus mod b is less equal mod of a minus b. Okay, so this is the first part of our example. Only to consider mod a mod b. If we consider mod a, then add and subtract b, and if considering mod b, then add and subtract b, and rearrange this all terms, we get finally mod a minus mod b is greater than mod of minus of mod a minus b. Okay, here multiply by minus 1, multiply by minus 1 on both sides, we get only sign changing, change the sign here, less equal is greater equal. Okay, this is third part. Now to show that sequence Sn mod of Sn has limit L if sequence Sn has limit L. Okay, so second part is, now we prove that, now we have to show, now we prove that, or now we have to show sequence mod Sn has limit L or converges to L. Okay, here firstly given that since sequence Sn has limit is L, that is sequence Sn converges to L. Okay, that is limit n tends to infinity, Sn is equal to L. So by using epsilon n definition, for all epsilon greater than 0, there exists n belongs to I, such that mod of Sn minus L, mod of Sn minus L is less than epsilon whenever for all n is greater equal n. So using above result here, using this result, mod of mod A minus mod B is less equal mod A minus B. Using this result, now here mod of mod Sn minus L and their mod is less than epsilon, okay, is less sorry mod of mod Sn minus mod L is less equal mod Sn minus L, okay. Result is says that, and this term is less than epsilon by mod of mod A minus mod B. Mod of mod A minus mod B is less than mod A minus B. Using this result here, right, using this result here, A is suppose that Sn and B is suppose that L, then mod of this is mod of mod Sn, this is mod of mod Sn minus mod L is less equal mod A minus B, means Sn minus L, and Sn minus L is less than epsilon, which implies that for all n greater equal n, which implies that mod of mod Sn minus mod L is less than epsilon whenever n is greater equal n, and therefore by epsilon n definition, mod of Sn is converges to mod L, that is limit n tends to infinity, mod Sn has limit is mod L, okay. So this is a proof of our example. This is very simple proof. Then next example, if P is polynomial function, if suppose that P is polynomial function, if P is polynomial function in suppose that third degree, okay, 3 degree given that polynomial function, that is P of x is equal to a0 plus a1x plus a2x square and a3x cube. This is a third degree polynomial. Given that this is third degree polynomial, then prove that limit n tends to infinity, P of n plus 1 divided by P of n plus 1 divided by P of n is equal to 1, okay, P of 1, where, so how to proving this theorem, this example solution, how to show. Here given that P of x is polynomial in the form of where a0, a1, a2, a3 is belongs to in set of real number. This is a0, a1, a2 are constant, okay. Let P of x is equal to a0 plus a1x plus a2x square plus a3x cube, okay. Then consider P of n, then P of n is replace only x by n, okay, means a0 plus a1 n plus a2 n square plus a3 n cube, and P of n plus 1 is only replace x by n plus 1, means a0 plus a1 into n plus 1 plus a2 into n plus 1 bracket square plus a3 into n plus 1 bracket cube, okay. Then consider limit n tends to infinity, then consider limit n tends to infinity, P of n plus 1 divided by P of n is equal to limit n tends to infinity put the value of P of n. P of n is a naught plus a1 into n plus 1 plus a2 into n plus 1 square plus a3 into n plus 1 cube and divided by P of n, a naught plus a1n plus a2 n square plus a3 n cube. Okay, a3 n cube. We get for denominator term, in this term denominator term, common n3, take common n3, n cube is take common, limit n tends to infinity. Okay, and above term is as it is, a naught plus a1 into n plus 1 plus a2 into n plus 1 bracket square plus a3 into n plus 1 bracket cube divided by, taking n3 is common, sorry, n cube is common, then remaining is a naught divided by n cube. Okay, here common term is not, so here common is n cube, then divided by n cube, a naught divided by n cube, because n cube into a naught by n cube is n cube get cancelled, remaining only a naught. Okay, in this way a1 divided by n square plus a3 divided by n, and here n cube common is remaining only a3. Okay, so only this writing in the form of limit n tends to infinity, n cube is divided by all term, so a naught divided by n cube plus a1 divided by n cube into n plus 1 plus a2 divided by n cube into n plus 1 square plus a3 divided by n cube into n plus 1 cube, and so divided by only this term, a naught divided by n cube plus a1 divided by n square plus a3, sorry, here a2 divided by n plus a3. Okay, only rearranging this n cube. Okay, then limit n tends to infinity, a naught divided by n cube plus a1 is as it is, here this term, here common n, then 1 plus 1 by n is remaining. Okay, here and n plus 1 divided by, suppose that this all are divided by n plus 1 divided by n cube, n plus 1 square divided by n cube, and n plus 1 cube divided by n cube. Okay, so here common term is when n cube divided by n. Okay, then here only remaining that 1 upon n square plus 1 upon n cube. So here term is common n plus 1, so only how to common this term, n plus 1 is n into 1 plus 1 by n. Okay, 1 into 1 plus n by n, then this term is how to common, when multiply by this n plus 1 divided by n into n get cancelled, remaining n plus 1. So in this way 1 upon 1 plus 1 upon n into n divided by n cube plus, for this here common term is 1 plus 1 upon n, 1 upon 1 plus 1 upon n bracket square, and here n square is common here, because their term is n square, first term is, because we get this n square is common, then n square divided by n cube is 1 upon n. Okay, means n square divided by n cube into a2 plus a3 into 1 plus 1 upon n cube into n cube divided by n cube, and so which is divided by a naught divided by n cube plus a1 divided by n square plus a2 divided by n plus a3. Okay, how to common this term? Because for one term, how to common this n? Because suppose that m plus 1 square, since n plus 1 square divided by n cube is equal to, if expansion of n plus 1 square is n square plus 2n plus 1 divided by n cube. Okay, n square is common, then 1 plus here 1 plus 2 into n divided by n square means n plus 1 upon n square. So this is a square of, this is 1 plus 2 by n plus 1 upon n square is a square of 1 upon 1 by n square bracket square and into n square divided by, and this n cube as it is. In this way, here common n square, we get a expansion of this all term. Okay, 1 upon 1 plus 1 plus 1 upon n bracket square, n square is common, n square divided by n cube as it is. In this way, similar in this way. Okay, so therefore for this remaining only limit n tends to infinity, a naught divided by n cube plus a1 into 1 plus 1 by n into n divided by n square remaining plus a2 as it is 1 plus 1 upon n square as it is, n square divided by n cube means 1 by n plus a3 into 1 plus 1 upon n bracket cube. Okay, bracket cube, and n cube divided by n cube is 1 and divided by a0 divided by n cube plus a1 divided by n square plus a2 divided by n plus a3. Okay, so limit is put here, limit n tends to infinity. Okay, this equal, and so putting limit n tends to infinity, we get, if we putting n tends to infinity, then a0 divided by infinity is 0 plus a1 into 1 plus 0, 1 by infinity means 0 into 1 upon n square 0 plus a2 into 1 plus 1 upon 0, sorry, their value is 1 upon n 0, their square into 0 plus a3 into 1 plus 1 upon infinity means 0, their cube divided by a0 upon put n cube, n is equal to infinity, then 0 plus a2 also 0 and remaining only a3. Okay, so here all terms are 0, we get only a3 is remaining. Okay, so therefore only here remaining is limit n tends to infinity, p of n plus 1 divided by p of n is equal to 0 plus a1 into 0 plus a2 into 0 plus a3 as it is divided by a3 is equal to a3 by a3 is equal to 1, and this is limit n tends to infinity, p of n plus 1 divided by p of n is equal to 1. This is a solution of our example. Okay, how to show this example? Only rearranging p of n and p of n plus 1. Okay, then next example is give an example of a sequence. Give an example of a sequence of real number for which sequence mod Sn where n runs from 1 to infinity, convergent but sequence sequence n runs from 1 to infinity. Modulus is convergent, but sequence Sn is not does not converge. Okay, or is not convergent, does not convergent. Give example of sequence. Their modulus sequence is convergent, but sequence is not convergent. How to give example here? Any example? So for this example, let n runs from 1 to infinity is equal to sequence minus 1 raised to n, where n runs from 1 to infinity. Okay, it has this sequence has two subsequences. Okay, this sequence has two subsequences, s2n and s2n minus 1, means which one sequence contains only 1 1 1 constant element, and second sequence contains only minus 1 minus 1 up to so on. This okay, and their modulus is if modulus of this sequence is 1, therefore this sequence is convergent. Okay, sequences in it has two subsequences. It has two subsequences, that is s2n is equal to 1, s2n is equal to 1, and when n is e1, and s2n minus 1 is equal to minus 1 when n is odd. Okay, so 1 is even and 1 is odd. This is two subsequence of Sn. Then elements of Sn. Okay, elements of Sn are what is the element of Sn is 1 minus 1, 1 minus 1, and up to so on. This is the content. Therefore their modulus is 1, because mod of minus 1 is also 1 and mod of 1 is also 1. Therefore their modulus is 1, and therefore this sequence s2n, mod of s2n and this s2n, this sequence is converged to 1. Therefore mod of Sn is also 1, means which contains only positive integer 1 1 1. Okay, therefore the sequence mod Sn, where n runs from 1 to infinity is convergent to 1. Okay, but we know that sequence Sn is not convergent, because it has two different subsequences has same different limit. Okay, we know that sequence Sn is equal to minus 1 raised to n, where n runs from 1 to infinity is not convergent, Okay, so modulus of this sequence is convergent, but given sequence is not convergent. Okay.